So once upon a time, data storage was simple. You just buy some drives, use a SCSI cable, plug it in your server, and life was good. Then we needed to share that storage. So we got some fiber channel switches and arrays, but it was still block storage directly to the servers. It was simple and effective, but not super functional. So soon it wasn't enough just to share those raw disks. We wanted to share them, we wanted them to be searchable, so we had to add metadata controllers and some indexing servers. And life was good again. But then one day, you got solid state disks. People had them in their laptops, they were fast, they started to expect more from their storage. So how do you build a SAN, or go from a SAN that uses a dedicated storage fabric to a platform that's scalable, works anywhere in the world, it's fast, it's reliable, and it doesn't break your CFO's heart? I'm going to just start with a few key concepts for building a modern storage platform. These are often in your marketing slides, but we're going to explain a little bit why they're important. So solid state storage, it's non-volatile flash memory. It's made of NAND chips, it's high density, has a relatively low cost. You start with SLC, which is single layer cells. They store 1 bit of data, they've got very high endurance, they last for years, but they're not quite so dense, and they are quite expensive. You can go all the way up to penta levels chips, but the most common ones you're going to see are TLC and QLC. They are higher density, they are lower cost, but if you write to them all day, every day, they're going to wear out in 12 months, so we've got to design around that. RDMA, Remote Direct Memory Access. This is a technology that allows servers and compute nodes to transfer directly from the storage through the network without involving the CPU or kernel. So your NVIDIA ConnectX cards and Spectrum-X networks, they really allow this, and it gives you a massive performance increase when working across Ethernet networks for storage. NVMe, or non-volatile memory express, is an interface to those solid-state disks that allows parallel access to your storage through the PCI bus. It's a huge performance increase over traditional SCSI or SATA. That can be extended with NVMe over fabrics. So using that RDMA networking, it allows machines to directly access across the network to the NVMe storage with nothing getting in the way. So RAM. Every computer since the dawn of time has had RAM, but there's different types of RAM. So you have your SRAM, which is like your CPU caches. It's really fast, but it's really expensive. DRAM, your traditional system memory, very fast, it's dynamic, but it doesn't retain information when the power's turned off. Then we have a newer technology, storage class memory, so it's non-volatile memory. Similar performance to DRAM, but the persistence of NAND flash. So that's going to be part of your modern storage. And then you can see on that graph, we have SSDs, and below that hard drives. The speed really decreases, but the price goes down. So it's a balance of power, volatility, and speed. Erasure coding, it's a data protection technique that encodes a single file into multiple fragments. You use K chunks to store the data, M chunks to store the parity. The chunks are stored across different storage pools, and it differs from your traditional RAID in terms of the data replication and mathematical algorithms. And as you can see in the diagram, you can use erasure coding across nodes and even across data centers, whereas traditional RAID, it's kind of stuck to a physical controller. Another new term, RAG, Retrieval Augmented Generation. So this is an architecture that allows AI LLMs access to external knowledge. So typically the file stored on your private storage repository. So the AI can search in real time your documents. So why do we need to change? Searchability is a big one. Big spinning disk arrays can provide some pretty impressive throughput, but simultaneous I/O latency isn't so great. With AI wanting to search in real time, you really need to improve the performance of your storage for that. Redundancy. So a typical RAID controller requires a rebuild when a disk fails. That takes time, that has a performance impact. And with the amount of data now in a modern storage platform, traditional RAID just isn't a thing. We have to build a smart, redundant system. Geo-tolerant designs. So businesses demand guaranteed availability of data. You used to think RAID protects my data, but what happens if you lose that whole rack or that whole data center? A few years ago, Brisbane had some big floods, whole data centers went underwater. You had a backup in the other data center, it was still in Brisbane. It was underwater too. So you really need to think about that. Users are on the edge of the internet. Gone are the days where storage would just sit at a powerful workstation, really plugged in to the users. Now people are anywhere in the world. They want to collaborate with teams on other sides of the world. And people want to work in the field and be able to work on that data immediately. AI workloads. So right now, 57% of traffic on the public internet is generated by AI bots. Traffic on your private network is increasing too as we get AI within the organizations. Searching those databases, customer records, and research data in real time is creating a tremendous load on storage resources that just weren't there a few years ago. So what's a modern storage platform look like? It's going to be really fast, utilizing storage class memory, NVMe SSDs across lots of nodes. Some workflows require high IOPS, some raw throughput, and often you need both. It's highly available. So you use erasure coding, lots of small nodes, which gives you that high network availability. You have multiple client entry points so that you can have users in Melbourne, Brisbane, they're coming in through their own entry points. And you use geo-spreading to make sure that data is across multiple locations. It's very scalable. You need to ensure that performance and capacity can be added at any time without downtime or a performance hit while the system rebalances. Sometimes you need to scale up and down. A lot of organizations will have a peak period of the year where you need more storage, but they don't want to pay for it the rest of the year. It's going to be compute ready, so processing directly in the storage platform to allow databases, AI agents, and other services to access that data without chewing up your client network. Cloud native. That typically means it runs on Kubernetes. It's storage software that can run locally or in the cloud, or both, so you can seamlessly move between them. It's got to be extensible, because being fast isn't enough. Users want access to all their data in one platform, so you need to use intelligent tiering to get from storage class memory to NVMe to spinning disk, and yes, even tape. You need to ensure that that storage platform can grow without costing the earth. So how do you build a modern storage platform? Unfortunately, there's no one holy grail. You can't just buy a product, plug it in, and it does everything. You need to ask questions of your users, your research teams, your other business units. How much do you need today? What's your annual growth rate? Important one is, where are your users located? And how do they generate the data? Do they process it all in the cloud? Do they ingest it from a field office? It's an important part of your storage design. What performance profile do your applications require? Do you have hundreds of small applications that all share the storage performance? Or do you have just a couple of big ones that are smashing it hard all day? How often do you access your archive data? Is it once a week, once a month? If you're accessing all day, every day, you need a way to ensure that that historical data is both cost effective and available. Do your storage requirements change through the year? Do you have just a 3-month peak where you need lots of storage and the rest of the year it's pretty small? For the techs out there, do you need a native file system client that has GPU Direct, or is something like NFS or SMB suitable? The latest modern storage systems kind of have a hybrid of both. Do you need any block storage still? So if you've got IT enterprise requirements, the VMs typically still want block storage, but your researchers will often want NFS. Can your data benefit from deduping compression? If there's lots of video data in there, probably not worth considering that, but financial records, customer records, they often do. What are the pain points of your current system? Everyone's got storage at the moment. How much time do your researchers spend waiting to access their data? How often do they repeat work? Like if something's in the archive and they can't search it, how do they repeat it just because they can't find it again? And do they have access to the data in the places they need it? So I'm just going to quickly run through a few broad stroke types of modern storage. So your super fast flash arrays. This is what you plug into an HPC cluster. Uses the fastest possible storage class memory and NVMEs, runs up to 800 gig switches. It's typically in the same rack as your compute nodes. So Vast Data Platform, Quantum Myriad, DDN, Infinia, there's a bunch of these out there. But they have some downsides. They're kind of slow or impossible to use from remote sites. You're not going to get 800 gig across multiple data centers. And the redundancy is only by asynchronous replication, so it's not a real-time mirror. Geo-redundant object stores. So typically your big web applications or backup targets, very high capacity, equal performance regardless of where you are. These systems, they normally talk in numbers of nines as far as the uptime goes, and they run across a 10 or 25 gig Ethernet. So Quantum Active Scale, Azure GRS, Scalability Ring, you can run these in multiple cities, same performance everywhere. It doesn't have the performance of a local flash array, and the cost to get started on something like this is pretty high, but then expansion gets cheaper. Software-defined storage. So this is something where the storage platform runs on any type of hardware. Weka Data Platform, NetApp ONTAP, there's a bunch of these out there. The challenge with this, it can be hard to build a high-performance system, or the redundancy. You saw AWS go down last night. That was just one data center going down, but it took out whole storage platforms because they didn't think about this. Then your archive platforms. So compliance, retention, and 10 years worth of research. Big organizations will have an archive. Is it a modern one? You typically will bolt this onto your super fast flash array, and it includes some kind of automation to offload from your high-speed, expensive storage onto these high availability but cheaper tiers. So Versity Scaled AM's a good example of this. HP DMF been around 30 years. A lot of people have been running it for 30 years. There's a few others out there, anything that's an HSM. The con of this, it is a lot slower, so you need that automation. It's also another platform to manage, so your IT staff, it's just another level of expertise that they need. Here's a real-world example that I worked on, an HPC research cluster with an archive. You can see at the top there, we've got the HPC nodes. It's running Vast Data Platform, C boxes for compute, D boxes for storage, storage class memory, TLC drives. It's running Versity Scout AM with an extended cache and SpectraLogic tape library. They use explicit archiving, so that is the users move it manually from the Vast flash storage onto the Versity hot disks. They then use an implicit archive where policy rules automatically move it from the hot disks onto tape, and then when it hasn't been used for 30 days, clears it off the hot disks. It uses a disaggregated design, so you can expand the compute, the flash, the hot archive, the tape archive all separately, so they're physically separate devices, and they can be scaled without impacting any of the others. They did have a geo-redundant design, so you use Versity policy rules to create additional copies to an offsite data center. So another rack looks kind of like this in another city, and it replicates between them. Security is super important in your storage. This one was very simple because it's all internal, it's an isolated network, but when you're designing those modern systems, storage security is super important. Now, there's some limitations to doing it like this. There was no erasure coding across geos, so it wasted a lot of capacity. The other data center used all the same capacity as this with no increase in usable data to the system. Also, no cloud capacity. So if they ran out of storage, they just had to buy more. You can't just burst up for a couple of months and then burst back down again. So that's modern storage. Any questions?
We have time for some questions. Any questions?
If not, come see us at the stand. We'll be there next 2 days.
Let me have a warm-up question for this one. So nowadays, used to be data growth is faster than the existing data storage capacity. One of your slides touched on the data archive. Any further tips on intelligent data archiving?
Yeah, so archiving is a super important part, especially in research. It's growing faster and faster every day. It might seem antiquated, but tape is still an important part of a modern storage platform. tape you'll never run out of. So don't discount it just because it's not as fast as NVMe.
Thanks, Pat.
All right, thank you all.